last time we ended on this problem, we had this 2 by 2 matrix, 1, 1, negative 1, 1, and we had to find all the eigenvalues and associated eigenspaces. We said that the eigenvalues are 1 plus I and 1 minus I, and we found the eigenspaces, and they happen to be the span of these two vectors. So the 1 plus I eigenspace is the span of negative I1, and the 1 minus I eigenspace is the span of I1. Now, I want to remind you of something I said a couple of videos ago, which was that if lambda is a complex eigenvalue for some matrix A, and X belongs to the lambda eigenspace, then I said that lambda bar, which is the complex conjugate, is an eigenvalue, and x bar, the complex conjugate of this vector, belongs to lambda bar, its eigenspace. And we can see that with this example. You see that we found two eigenvalues, 1 plus I and 1 minus I, and they're complex conjugates. And any vector in the 1 plus I eigenspace is a scalar multiple of this basis vector. And you can see that the complex conjugate of this basis vector is right here, I1. So if we had something like negative 3i3, that's just this one being multiplied by a 3, if you take its complex conjugate, this should be a 1, excuse me for that. No, it's not a 1, it's a 3. Okay, so what I did was I multiplied this one by a 3, and I got negative 3i and a 3. So this belongs to the 1 plus I eigenspace, and you can see that its complex conjugate is 3i3, and that belongs to this eigenspace. So what I said from that video, you can see that it's true with this example. Let's move on. Let's talk about something really interesting, and that is there's a relationship between the determinant of a matrix and the trace of a matrix and the eigenvalues. So here's a fun fact. Suppose we have an n by n matrix that has these distinct eigenvalues, and the eigenvalues come with multiplicities. So for example, the characteristic polynomial will look something like this. Well, if you have this characteristic polynomial, so you got distinct eigenvalues and multiplicities, you can find the determinant of your matrix. But the determinant of the matrix is actually going to be equal to the product of the eigenvalues raised to their multiplicities. So it's equal to lambda 1 to the m1 times lambda 2 to the m2, all the way to lambda k to the mk. Here we found the eigenvalues of this matrix in the last video. So recall that for this particular matrix, the characteristic polynomial is lambda minus 1 plus I to the first power times lambda minus 1 minus I to the first power. You can see that we have two eigenvalues, and they both have multiplicity 1. Let's take the determinant of this matrix. The determinant of this matrix is 1 times 1 minus negative 1 times 1, which is 1 minus a negative 1, which is 2. So I claim that this is equal to, let's see if it's true, 1 plus I raised to the 1 times 1 minus I raised to the 1. That's what I have written here. We take the eigenvalues and raise it to their algebraic multiplicities. Is it true? Well, this is equal to 1 plus I times 1 minus I. FOIL this, you get 1 minus I plus I minus an I squared. These i's cancel, 1 minus I squared. Since I is the square root of negative I, then this is 1 minus negative 1 because you're squaring I, so you get 2. So you can see that these are the same. I want to show you another example of this. This was actually a matrix we did a while ago. This is an upper triangular matrix. And if you look back in your notes, you can see that the characteristic polynomial for this matrix was negative lambda minus 1 squared times lambda minus 2. So the eigenvalues are 1 and 2, and the algebraic multiplicity of 1 is 2, and the algebraic multiplicity of 2 is 1. Let's take the determinant of this matrix. Well, it's an upper triangular matrix, so the determinant is just 1 times 2 times 1, which is 2. And now let's see if we take 1 raised to the 2 times 2 raised to the 1, if we get this number. This is just 1 times 2, which is 2. So we get the same thing. And this works for any matrix you put here. So we've looked at a 2 by 2 and a 3 by 3. We looked at an example that had complex eigenvalues. Here's an example that has real eigenvalues. So it'll work no matter what type of matrix you have, as long as it's, square matrix. I mentioned that there was a property involving the trace of a matrix. I don't think we've talked about trace before in this class, so we're going to define it right now. The trace of an n by n matrix A, so this only works for square matrices, is just the sum of the diagonal entries. So whatever's on the diagonal, you just add them together, and that's the trace. So if we have an n by n matrix, and we have distinct eigenvalues with certain multiplicities, again, we can write the characteristic polynomial as lambda minus lambda 1 raised to the m1, lambda minus lambda 2 to the m2, and so on. Let me move this over. So if this is our characteristic polynomial, then the trace of the matrix A is just the sum from I is equal to 1 to k of mi times lambda I. So it's very similar to the product formula, except for we're not raising it to the power, we're actually putting the power in the front. So this is m1 times lambda 1 plus m2 times lambda 2 all the way to mk times lambda k. So instead of putting the power up here and then multiplying, we put the power as a constant in the front of this lambda and then add. Let's see if that's true with a couple of examples. We're going to look at the same examples we did a minute ago. So the trace of this matrix, all we do is we add these two together and we get 1 plus 1 is 2. And let's find the trace of this matrix. The trace of this matrix is 1 plus 2 plus 1, which is 4. Okay? Now let's see if we follow the property above, that the trace is just the sum of the eigenvalues multiplied by their multiplicities. We said that the characteristic polynomial for this matrix is lambda minus 1 plus I raised to the first power times lambda minus 1 minus I raised to the first power. Here are our eigenvalues, here are multiplicities, so we just say 1 plus I times 1 plus 1 times 1 minus I. This is 1 plus I plus 1 minus I. The i's cancel, and we get 2. So we get the same thing. Let's try it with this matrix. So the characteristic polynomial was negative lambda minus 1 squared times lambda minus 2. So we're going to take 2 times 1, the algebraic multiplicity times the eigenvalue, plus, this is raised to the 1, so 2 times 1, we get 2 plus 2, which is 4, which is exactly what we have for the trace.